Hi, so welcome to my YouTube tutorial. This one is going to be on, we're going to switch over from Xilinx and we're going to use Quartus Prime and the Altera FPGAs, and we're going to output a little guy or a girl, whatever you want to do, this little face over VGA. So this video assumes that you have some experience using VGA. If you do not, no problem. I think it's really cool. VGA stands for Video Graphics Array, and I am going to link a video in the description below that is from a channel called Simply Embedded. Fantastic video, and he goes over just a super simple VGA controller, and I would highly advise you watch that. Even if you haven't, even if you know VGA and maybe haven't used it for a while, go and watch that and just get a little refresher. This figure actually right here is from his video, so credit to him for that. Without further ado, let's get into the video. So we're going to be doing a 640 pixel by 480 pixel picture, so 680 vertical by 640 horizontal, right? Or also known as 480p, and at 60 FPS, which means frames per second. For that we need a 25 megahertz clock, and I'll go over that later. But in this timing diagram, it's a little confusing because it says addressable video time 640 pixels, but we see this pixel count goes from 144 to 783, right? Just a note on this graphic. This is 784, but it's on the right side of this little bar. So on the left side, that pixel would be 783. So that's what I wrote here. So to adjust for blanking and addressable video time, the counter values really are going to go from 144 to 783, and that's going to be our valid data output window, and that length lasts 640 pixels. Yes, but there is some other pulses going on, like the VSync or the VSync down here for 2 pulses and the HSync for 96 pulses, things like that. And the VGA video goes over all that. Like I said, watch that if you want to. Great video, great channel. So let's go over some of the code, not all of it yet, but I have my port declarations up here. So I got clock, I have the horizontal sync, the vertical sync, I have the output red, the output blue, the output green. The module is called Smiley Test. It'll be linked. This code will be linked in the description. It'll be a link to my GitHub. And it's called Smiley Test because I'm going to be using it for something else later that I'll make a video on as well. Note that my input clock is 50 megahertz, which I said what we actually needed was 25 megahertz, and we'll talk about that later, okay? So if your clock is different than 25 megahertz, don't worry about it. We can talk about it later. The registers that I have one for the horizontal counter called counter X, one for the vertical counter called counter Y, and then I have some each for the colors, right? Each 4-bit colors. This reset register, that's for the PLL phase lock loop. We can talk about that later. And we're going to ignore this clock section right now. It's a clock divider, but we will go over it later when we get into the Quartus software. And let's go to the counter and the sync generation. So always at pause edge clock 25 megahertz. This is from the PLL, the clock divider, which again we will talk about later. So we're going to count 0 to 799, right? That's 800 counts. And I'm going to maximize this actually. Then we have increment the counter if it's less than 799, obviously, yes. And otherwise make it 0. So that's pretty easy for the horizontal counter. For the vertical counter, it's a little bit different because we have to wait until the horizontal counter is finished completely with a full line of pixels to count up 1. So if the horizontal counter or counter X is 799, meaning it's finished, then increment counter Y as long as counter Y is less than 525. Otherwise, counter Y resets, right? So it'll only reset or increment when the counter X finishes. So that goes over the horizontal and vertical counters. If we get into the horizontal and vertical sync down here, As if you look back at the timing diagram, we see the horizontal sync is high for 96 counts at the very beginning, and the vertical sync is high for 2 counts at the very beginning. So just like this is what this says. I suppose I could simplify this line just to say counter y less than 2. Actually, let's do that right now, just to, yeah, like this. Counter y is less than 2, right? And we can simplify this guy right here, actually. So, boom. Oh, not what I meant to do. Whoops. Actually, we'll just keep everything the same just for continuity's sake. So don't do anything. Just know, yes, you could simplify it. Bad timing on my part, or bad code writing. But as long as it's less than 96 for the horizontal counter, then the horizontal sync is going to be 1 or high, and otherwise it's going to be 0, right? So it's high for 96 counts. Similarly with the VSync, as long as the vertical counter is less than 2, then we're going to output a high, otherwise output a low. So it's just going to be a little pulse, okay? If we go down, and the next section is we're looking at the pattern generate. So the pattern generates where we generate our face, and we're not going to talk about that right now. So we're going to go all the way down to our output assignments, right? So we're only going to output the colors when the counters or the pixel counters are within the addressable video space. So if we go back to our timing diagram, the addressable video space is from the pixel count 144 to 783 for the horizontal and 35 to 514 for the vertical. And that's exactly what you can see here, right? The vertical count is between 35 and 514, and the horizontal count is between 144 and 783. So as long as we're in between those, we can output the colors. And if we are outside of those, then we're just going to output a 0. Okay, let's get into the smiley face generation. I guess it's not really smiley face, but it's more of a guy. I am going to try to explain this well, and just know it's a little bit difficult. It's a little abstract, so if you're confused, you can put something in the comments below and we will talk about it, okay? So I tried to think in terms of addressable video pixel count time for the horizontal and vertical counts. So if this is going to be our screen, right, the counter, actually, sorry, if this is going to be our screen, then we're going to have a little yellow spot in the middle. For the face, we're going to have 2 eyes, and we're going to have a mouth, right? The vertical count is going to start at 35, and it's going to end at 514, again, for the addressable video pixel time thing on the timing diagram. The horizontal count is going to go from 144 to 783, again, for the addressable video time, right? So that's going to be when we're going to want to output our data. So I used those as asymptotes, sort of, or like cutoffs within the code. What I did next is I broke up this smiley face into vertical sections. So we have this top section of the screen where it's just white. Then we have the forehead section of the face. Then we have the eyes. Then we have the middle section of the face. Then we have the little mouth. Then we have the chin. And finally, we have the bottom of the screen. So I broke those up and I added various thicknesses, and we'll go over those. So, whoops, one too far. So from 35 to 135 on counter Y, we're just going to want to output white. So as long as the counter is less than 135, we're going to output white because, again, the output assignments at the bottom of the code, they'll take care of this asymptote right here. Then, so that's the top part of the screen. And in the second section, I can go 1, 2. In the second section, we get to the forehead part. And we're like, okay, well, that's cool because we have a white, and then we have some yellow for the forehead, and then we have white again. But it's like, well, when do we know how to output each of those colors? And for that, we're going to use the horizontal counter, okay? So I'm going to go through and label all these sections. We have 3 is the eyes, 4 is the middle of the face, 5 is the mouth, 6 is the chin area, 7 is the bottom white space, And here is what defines all those different sections are these counter values for the counter Y, the vertical counter. To know which colors are going when, we have to use the horizontal counter. So I have that the yellow starts at 324, the eyes and the mouth both start at 371, the first eye ends at 383, the second eye starts at 545, and the mouth and the second eye both end at 557, just to make things simple. And then the end of the yellow is at 604, okay? So one example of this is, let's try looking at section 2 in the code. And we're going to go over it really quickly here. So in section, where did my mouse go? In section 2. So section 2 on the vertical counter is going to go from 135 to 205. So counter Y is going to go from 135 to 205. I'm going to pull up a little image right here, and we're going to stick this guy right there. And we're going to go up to section 2, which is right here. And you can see I labeled them in the code, and it's not showing it right now just because of the screen size. But so section 2 is going to start on line 76 right here. So section 2, just like what I just said, if the counter Y is between 135 and 205, 135 and 205 right here, section 2, then we can start outputting our different colors. So for here, we are in section 2 and we're at the horizontal count of 144. So as long as the horizontal count is less than 324, all we need to output is this white color right here. So that's exactly what the code says. If the counter X is less than 324, output the white color. Now we have the white and we have this yellow section right here. And that we can use these horizontal counter values to see the yellow section goes from 324 to 604. So that's the next little part of section 2. Is we have, if the horizontal counter goes from 324 to 604, then output the yellow color. And yellow is a mix of red and green. So I put 4-bit hex F for red and 4-bit hex F for green. So that's easy. Then we get to after 604. So if counter X, or the horizontal counter, is greater than 604, then we output the white color. So again, all 4-bit hex F for all the colors, and that's how we would do that section. Okay, so I encourage you to pause the video at that time and go over what's happening in section 3, because that's definitely the hardest one. And if you can get that, then you should be good to go. If you can't get it, put a question in the comments below and I'll try to answer it. And you can pause the video, maybe take a picture of this or a screenshot, something like that, and see how it goes. So for now, we went over the code and I went over an example of one of the sections, and you can see I have the ends of the sections marked and the start of the section, so you can go over that easily. And I will pause the video right now, or actually I'm going to start a new video, and we will go over what's going to happen within Quartus Prime. Okay, so I'll see you then. Bye-bye. Okay, so I have Quartus Prime opened up, and the board that I'm going to be using is called the DE10 Lite from Terasic or Terasic. I'm not sure how you say it, one of those ways. It has a Max 10 FPGA on it. So I already went ahead and I created a project for this. And if you don't know how to do that, I can link a user guide in the description below. So Altera or Intel rather they have pretty good user guide. I think I prefer Xilinx's better, but it's up to you, you know. So I'll link one of those in the description below. So we already went over most of this code, but I said that we would have to tackle this little clock problem. What we need is a 25 megahertz clock, and we have a 50 megahertz clock, or that is my input clock. Yours might be a little bit different. So how do we do that? How do we get a clock divider? And the way that I did it is you go over here and to this IP catalog, and you can expand this basic functions, and you can expand this clocks, PLLs, and resets, and expand the PLL and double click on the Alt PLL. It's going to want you to select an IP variation name. So we're just going to call this YouTube example. Maybe you would want to call it clock divider 5225 or something like that. Variation file type, I'm going to be using verilog, so I'm going to click OK. And then it's going to take you to the PLL wizard, or the mega function wizard. You can put in what is the frequency of the in clock 0 input. So my in clock would be 50 megahertz, 50. It says able to implement the requested PLL. Yes, okay. And all of these defaults were fine for me, so I'm going to click next. And additional inputs, on mine, I just kind of went through and just used all the defaults. So you can create a locked output. You can uncheck this to not use a locked output. You can use an asynchronous reset. I think the reset's active. Might be active high, I think. So yeah. And so I just left these checked. Click next, and I left that fine. If you want to use a second input clock, you can. I didn't. I clicked next on this because I didn't need anything. So C0, that's the external clock, and this is the clock division factor. This guy is what we really care about. We're going to increase that to 2, and you can see this actual setting is output to 25.0000 megahertz with a 50% duty cycle, right? Then we're going to click next. We're only going to be using one other output clock, so C1, C2, C3, and C4. We're not going to be using. Click next, 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 and next, and then we can create finish. Now I already created finish, and what that does is it can add so I'm not going to click finish. It adds this little ip.qip folder or file thing, and that contains is your PLL verilog file. So what I did is I opened that up and I looked at the ports, and I was like, okay, well, this makes sense because it was what I told it to do. So this is a clock divider from 50 megahertz to 25 megahertz. So I instantiated that because I just called it IP, which was not very descriptive, but for this project it's fine. So I just called it IP, and I instantiated that within my my Smiley test module, which is the top level module in the design. So I have a 50 megahertz clock coming in, so that's where I put in clock 0. For the reset, I just have that low tied to this low register reset. That's what that was for. I could have not used that input, and maybe I should have used that. The clock 0 or C0, that's our output, which is clock 25 megahertz, and that is what all the sequential always blocks are. That's what's in the sensitivity list. The locked output I chose not to use, so that's how I instantiated that. Once you have that all good to go, so that one might not work for yours. If you have a 50 megahertz clock in yours, then totally go for it. It'll totally work. I'll include this ip.v file inside the GitHub repository for you. I click compile design, and we can open up this program device. Okay, so once you've got your board programmed, this is my FPGA board. And one thing I forgot to mention was to make sure your I/O constraints or your pin constraints are mapped to the correct VGA pins, right? That's pretty important. The VGA is going around back through that mess into the TV, and if we look at the TV, we have a little cute face. And I hope you enjoy this project, and have a good week. Bye.